So in this video, we're going to talk about Avogadro's law. Basically, it describes the relationship between volume and molar amount. So Avogadro's law, which is named after Amadeus Avogadro, where it describes that the volume of a gas is directly proportional to its molar amount at constant pressure and temperature. So when pressure and temperature is constant, the volume, all right, is dependent on the molar amount. So the more moles of gas you have, the greater the volume. That's essentially what it's saying. And the less moles you have, the lower the volume. So interesting enough, there's a really interesting pattern that is found when it comes to Avogadro's law and volume. Okay, and so for example, and what I mean by this is that if the conditions in which the gas is in is at STP, all right, and so what does this mean? Is that standard temperature pressure. So at STP or standard pressure, it's when you are at a very specific temperature and very specific pressure, okay? The temperature that we're talking about has to be 0 degrees Celsius or 273 Kelvin. All right, and the pressure that we're referring to, it's at 1 atm or 760 millimeters mercury. Okay, so when we say something's at STP or standard temperature pressure, we're saying specifically that the temperature is 0 degrees or 273 degree Kelvin, or and the pressure, not or, but and the pressure is 1 atm or 760 millimeter mercury. Okay, when this is the case, all right, the volume of that particular gas, all right, and which we will coincidentally call standard molar volume at STP, all right, the volume of any ideal gas is 22.4 liters per 1 mole. Okay, and so if you have 1 mole of any gas, okay, so at STP, if you have 1 mole of any gas, all right, at STP, the volume of that gas is going to be 22.4 liters. Okay, and this is a really interesting relationship, all right, because then we could kind of look at this. And so, like, for example, if you have 1 mole of oxygen at STP, all right, well, what do we know? Well, we know that we have 1 mole of oxygen. Okay, we know the mass of oxygen due to the atomic weight. We could look at the periodic table and we see it's 32 grams. All right, and then we know the volume to be 22.4 liters. All right, so we could do some really interesting conversions going between moles, mass, and volume as long as we're at STP. All right, same thing if we had like 1 mole of helium. All right, so 1 mole of helium at STP. Well, we know what's the mass of helium. All right, if you look at the periodic table, if it turns out to be 4.00 grams, and then the volume of helium, if it's at STP and you have 1 mole of it, is always 22.4 liters. Okay, same idea with, same idea with fluorine. All right, if we had F2 at STP, okay, we know the molar mass of F2 when you look at the periodic table is 38.0 grams roughly, and then the volume that the amount of fluorine that would take up is going to be 22.4 liters. Okay, and then we could do one more example. If we had 1 mole of argon, all right, the noble gas argon, all right, and if we're talking about at STP, where the temperature is 0 degrees Celsius or 273 Kelvin, the pressure is 1 atm or 760 millimeter mercury. All right, the molar mass of this is roughly 39.9 grams, and the volume is 22.4 liters. Okay, and so this is the relationship between moles, mass, and volume as long as we're at STP. And just remember, overall, 1 mole of this substance is equal to 6.02 times 10 to the 10 to the 23, or actually more like 6.022 times 10 to the 23 of that particular substance. All right, so just kind of keep in mind that relationship. And so if we are talking about something at STP, okay, then, and if you're talking about, like, for example, oxygen or helium or anything, any of it really, where we have 1 mole, all right, is equal to the atomic weight in grams, right? And we could find that from the periodic table, which is in grams, all right, which is also equal to 6.022 times 10 to the 23rd of that substance, which is also equal to 22.4 liters. And this right here, we call it the molar volume, okay? Much like here, we call this the molar mass because it's grams. This right here, we call it the molar volume because it's in liters. So let's look at an example problem. So using the standard molar volume of a gas at STP, which is 22.4 liters per 1 mole, to find how many moles, so we're looking for how many moles of air at STP are in a room measuring 4.11 meters wide by 5.36 meters long and 2.58 meters high. All right, and so we're trying to figure out how many moles of gas at STP is taking up this much space. Okay, now if you recall from K through 12 math, right, volume is equal to length times width times height. All right, and so I gave you the length times width and I gave you the length, width, and the height. So to find the volume, you just have to multiply these 3 numbers. So 5.36 times 4.11 times 2.58. All right, and so if you multiply these 3 numbers together, we will get, and these are all in meters, right? So we'll get 56.8 meters cubed. All right, now if you recall that 1 meters cubed is equal to 1,000 liters because the volume must be in liters for us to use molar volume. All right, and so we're going to use this relationship to convert from meters cubed to liters. All right, and so basically I'm going to have 56.8 meters cubed times, we know for every 1,000 liters is equal to 1 meters cubed. So that will cross out meters cubed. 56.8 times 1,000, all right, is essentially 5.68 times 10 to the 4th liters. All right, so now we have this in liters. Okay, so now what we're going to do is figure out how many moles of air will take up this much space. All right, well, what's the relationship we know? Well, we know that for every 1 mole of air at STP specifically takes up 22.4 liters. All right, and we're trying to figure out how many moles, right? That's what we're trying to figure out. So we could use this to use this conversion to help us to get from liters to moles. All right, so we have 5.68 times 10 to the 4th liters multiply. So we'll put liters on the bottom, moles on the top. Using this relationship, we know that for every 1 mole of air is 22.4 liters. All right, so you put this in the calculator accordingly, and we'll get that you will have about 2.54 times 10 to the 3rd moles of air that will occupy this space. Okay, and so this is just kind of one way that this is an example of how we could use the molar volume to either convert from moles to liters or liters to moles.